I would like to thank the organizers for a chance to attend this conference and to give a talk. And also, I would like to start with mentioning that this is a joint work with Iran Calvert, Andrei Krutov, and Pavle Panjic. So this one is the only one you didn't get a chance to meet today, but he kind of joined in to try to generalize this stuff a bit more, so not just to the k-primary case, but I'm not going to talk about that. I will start with semi-simple complex algebra G. And let's take its Cartan decomposition. So K plus P. So this K is the same one here. And I will need a Cartan subalgebra, but I'm not going to take just any Cartan subalgebra. I'm taking the fundamental Cartan subalgebra, which, as denoted by H, would be the one that decomposes as T plus A, where T is a Cartan subalgebra for K, and A is completely inside of P. Also, I need orthogonality, so let's take B to be a non-degenerate symmetric invariant bilinear form. So if we're working with the semi-simple algebra, it would just be the killing form. And this bilinear form, first we can restrict it to P, and then using a determinant, extend it to the exterior algebra of P. Why do I want to do that? Because the space I'm interested in are the k-invariants in the exterior algebra of P. Now, you might be wondering, why am I telling you about this? Why would we want to hear from this little girl coming from representation theory? Well, there is a geometrical interpretation for this guy here, even though I'm studying it for different reasons. But if we replace all of these Gothic letters with capital Latin letters, meaning we go back to the Lie groups, then we have that the cohomology of G over H is exactly k-invariant part. Sorry? Yes, sorry. Is exactly the k-invariant part of the exterior algebra of P. Now, I won't be looking at all the cases. I'm interested in this so-called k-primary case. Right, first of all, we are not interested in the usual G age roots, but we can look at the restricted roots. So I'm not taking this Cartan subalgebra for G, but I'm going to be looking at it with respect to this smaller subalgebra. So this Cartan subalgebra of K. So the roots I'm interested in will be GP and KT. And of course, these roots are inside of these roots. And if I denote by WGT the Weil group with respect to these roots, and analogously KT, the Weil group for KT roots, then we can quotient it and we get a coset of Weil groups, which generally speaking is not a group because this is not a normal subgroup here. And my assumption is that this is just one element, which has a lot of interesting interpretations in the terms of representation theory, but obviously I'm going to skip that part. Let's say the spin adjoint representation is primary, so a few copies of the same irreducible representation, that would be one of them. Now, I promised to give you something called transgression. What is a transgression? It's a really nice map that should end up in this space. However, in order to construct a map, first we need the domain. So now let's get to the domain. Let's define the relative Weil algebra as k-invariants in the tensor product of symmetric algebra of G and the exterior algebra of P. Now, this is the definition and I will lead it, but there is a way to define this guy here in a way that would be a bit more suitable for this conference. So we can look at the so-called absolute Weil algebra. So take all the letters. No, wait, I'm not talking about invariants at the moment. So the absolute case is replacing all the letters with G. Now, this algebra is a G differential algebra and therefore a K differential algebra. So we can look at its K basic subalgebra. It turns out it's exactly the one I need. Okay, nice. Now I also will need a projection. So this relative Weil algebra can be decomposed as, well, take the exterior part and add the rest. That would be G considered as injected into the symmetric algebra and multiply. K basic. It means that those are the elements that are killed both by contractions or by elements with K, and that part is the so-called horizontal part, and also that they are k-invariant. So killed by Lie action and contractions with these guys. Okay. And no. So I will need a projection from the whole algebra to this exterior part with respect to this decomposition. And let's denote that projection by pi. Now, since this guy here is an ideal, this is a homomorphism. Great. Since we're speaking of differential algebras, I should also mention what differential I'm talking about here. My differential is, for those of you who wonder, the sum of the so-called Chevalier-Eilenberg differential and Kožul differential. So finally, let's get that domain of the transgression. Now, since we have this orthogonal decomposition, it induces, and we have this orthogonal projection from G to K that induces some projection in the symmetric algebras. So, and here comes another moment where I can mention something interesting to us. As I said, I have this assumption of the K-primary case. Only in this case, not in general, is this projection surjective. And it has an inverse, and the inverse will be precisely what is usually called the characteristic homomorphism. So if we have a connection on G and the connection of K on K and extend it to the level of Weyl algebras, this inverse is precisely the characteristic homomorphism for this pair. Okay, great. We have surjections. And okay, let's denote it like symmetric projection. The domain of my map will be exactly the kernel of this map. So precisely the guys that project to 0 here, meaning that each term has at least one factor from P. Okay, and I'm not going to talk about the formula for transgression, but you can see over there that it really needs this assumption that we have something from P in each summand. I'm sorry, this is not my water. Because it's, sorry? No. Well, no, because I have normal water and this is mineral water. And that makes me thirsty. Much better. Also, let's mention that the cohomology of the relative Weyl algebra is equal to SKK, which I also need to define the transgression. So this T will be called the transgression space, and it will be the domain of my map. So far, we have this. So we start with the whole Weyl algebra. I define the projection to the exterior algebra of P, and we have the differential. Now, what about this guy? It is super easy to see that the differential kills this whole space T. What is not so easy to see, but you will have to believe me, is that this T is also in the image of the differential, which means for every element here, we can find some element here that will match. And I'm going to need one of those. And then we define the transgression as the map that makes this diagram commute. Of course, one needs to check that it is well defined, that it does not depend on the representative we take here, and so on. And now comes the part, well, the main theorem. And I have to admit that last time some of you heard me talking about this was in January in Crni, and over there I said something wrong. And it was fixed later. So if we are looking at the absolute case where all the letters become G, then this guy is the symmetric invariants of strictly positive degree. And then over there, it turns out that the kernel of the transgression is precisely the square of this. So what we thought is that the same statement will hold true in the relative case, meaning that this will be the kernel. It turns out it's a bit bigger. So not this, but this. And that's one part of the transgression theorem. So the first statement is that the kernel of the transgression is precisely this, and the other one is talking about the image. So we know that the image is over here, but actually it turns out to be a very special subset called the primitive subspace. Now, what is a primitive subspace? Well, okay, to define it, I need to know which guys are orthogonal. So you take all the invariants of positive degree, take the square of that set, and then take the orthogonal complement of it inside of the positive degree invariants. But I have a really nice little story to describe them in a way a second-year student of math could understand it. So you know how every natural number is a unique product of prime numbers? Well, this thing is somewhat similar, meaning that all the invariants can be decomposed in a way that all the ingredients come from here. Now, if you would be so kind to tell me how much time I have left. 10 minutes. Perfect. Because just in case I end up having some extra time, I wrote down a really, really simple example to show you what it looks like explicitly. So not only like small example, I would say the smallest example possible. For this assumption, basically think about SLOD with K part being SO odd. And let's take the smallest odd number, positive odd number, that gives us anything one could be interested in. So the correct answer would be 3. So my Lie group will be SL3, and the corresponding maximal compact subgroup will be SO3. And now, as before, denote by G the complexification of the Lie algebra of G, and K will consist of real anti-symmetric matrices. The Cartan decomposition, the Cartan involution, which will define this decomposition, is the one that is most commonly used, so just minus X transpose. And in this setting, the dimension of K is 3, and the dimension of P is 5. Now, here it's important to notice that the dimension of P is odd, and some of the proofs in this whole theory are separated into cases when this dimension is even or odd. Again, the main reason is what is the spin module in one or the other case. But I will make another comment about it in a minute. Now, G invariants in the symmetric algebra of G are generated by 2 elements. I will denote them as P2, P3. Those are my symmetric primitive generators. Why P2, P3? Because those generators are of pure degree 2 and 3. So the index denotes the degree. Since I was talking about the smallest case, why 2 of them? Why not 1 of them? Well, the thing is, we can completely forget about this guy. Why? Because it won't be in the domain of the transgression. Meaning that this one has some summons that purely come as products of elements of K. So that projection, symmetric one, is not going to kill this guy, but it is going to kill this guy. And so P3 will be like some product of 3 elements of G plus some product of 3 elements of G, and so on. Now, the transgression is going to kill some of them, but not all of them. The terms that could survive the transgression are the ones that have precisely 1 factor from P and 2 factors from K. You might be surprised to learn that this conclusion is actually a consequence of some integration. Okay, now, what is the image of this element? Well, it's the only thing it can be up to a constant. First, let's mention that k-invariants in lambda p are 2-dimensional. So pretty much the smallest thing possible, constants, and the top degree of lambda p. So what's the top degree? Well, it's just that you take some basis for p, let's denote it by ei, and take the wedge product of all of them. And that, in this case, yes, that's what I promised to say, is why it is important here that P is odd dimensional. Here, okay, sorry, I'm writing this too generally. This, the product of the basis elements in P will always be k-invariant, but it will be a primitive invariant, maybe, only in the odd dimensional case, because it turns out, so this is of degree 5, but if this guy here was even, this would be of even degree. And it turns out the primitive invariants can only be of the odd degree. To compare it, okay, let's just denote this in case you haven't guessed already. The transgression will send P3 into some constant times the top element. And we actually don't know the constant because there is also an explicit formula for the transgression, but that's not very important. So why this is not always a primitive invariant? Let's take the next case. SL5. Here, P will have, dimension 14. And k-invariant part of lambda p will have dimension 4. So again, constants, the top guy of degree 14, and two primitive invariants of degree 5 and 9. And that one of degree 14 will be just the product of these two. And I believe that was everything I wanted to say today. So thank you very much for your attention. Don't forget,